Hello, and welcome to Acoustics Derivations. In this video, we will be deriving the conservation of mass as we work our way to deriving the wave equation for waves in a fluid. To derive the conservation of mass, we'll consider a control volume fixed in space with some arbitrary volume V and some arbitrary surface S. We note that the outward normal is N, and we can consider a differential element ds, such that we can write ds vector is equal to n vector times ds. We also note that the fluid in the control volume has some density rho. Now, it's really, for me personally, when deriving these continuity equations, it's very helpful to write them out in word form before you actually do the derivation. As such, we'll do that here. So the conservation of mass equates the time rate of mass increase in the control volume equal to the net mass inflow. Highlight that. We'll come back to that shortly. So the net mass inflow through the surface S. Okay, so that is our verbal word statement of the conservation of mass, otherwise known henceforth, maybe not henceforth, but I like to call it continuity equation. So I will likely be calling it that henceforth. So let's take this piece by piece. So what is the mass in V? Well, that's simply the volume integral of the density, right? Well, then the time rates of mass increase is simply the time derivative of that integral. Well, since V is arbitrary and fixed in space, it doesn't depend on time, we can move the time derivative inside as so. So that's our time rate of mass increase in the control volume. So what is the mass flow? Well, we can think of the mass flow as the density, or we can, well, it's a mass per unit time, and that can be represented as a density times the particle velocity times the surface you're flowing through, which in vector form would be rho times u dot s, which of course we can write as rho u dot n s. So that's our mass flow. And if you check the units, it'll check out. But I made a big point about net mass inflow, and this is just mass flow. Well, it turns out that if we want mass inflow, so we're specifying a direction we want, we actually have to put a minus sign up front. Why? Well, good question. Let's consider some part of our control volume where the outward normal is facing down, but the velocity is flowing in. If we so we want the velocity to flow in because we're looking for mass inflow, but if we dot u and n together, that's going to give us a negative number because the vectors are pointing in an opposite direction. But we know the fluid is going into the control volume, so we need to put a minus there to make sure it's a positive. That going into the control volume here is positive. Now suppose that we either change the part of the control volume we're looking at or we let the fluid flow the opposite direction, so it's in the same direction as the outward normal here. Well, if we dot those together, we see that U dot N is a positive number, but that's flowing out of the system, so it's negative, which is what we expect. Now, we want to look at it for an arbitrary surface, so we can write this as the integral of rho U dot N ds. Okay, so now we have the two components that we need here and here, and we can write an integral. So we can write the verbal statement in terms of math, and I'm going to put that on one side and set it equal to 0. So we have the volume integral of the time derivative of density plus the surface integral of density times particle velocity is equal to 0. So this is the integral form of the continuity equation. Okay, but it's important to put this in terms of in a derivative form, because that's how we derive, or we use the derivative form to derive the wave equation, and that's what we're really after here. Okay, so we need to recall the divergence theorem. Divergence theorem, which states that the surface integral of some arbitrary vector field can be written as the volume integral of the divergence of that vector field. So we're going to let rho times u be equal to a, such that we can rewrite, well, so we can rewrite the surface integral of rho times u dot n ds as the volume integral of the divergence of rho times u v. Okay, so we can then put it back into our expression up here, the integral form. And because they're both integrals over the volume, we can write it as one integral as such. Now, it turns out that the only way for this expression to hold for any arbitrary volume, and remember the control volume is arbitrary, is if the integrand is 0, which gives us that the time derivative of density plus the divergence of density times particle velocity is equal to 0. Let me clean this up just a smidge. Now, this is what we were after. This is the derivative form of the continuity equation. Okay, that concludes this video. Thank you.